An example that says maybe how much energy does it take to change lead from, I don't know, what's lead's, let's see what lead's boiling point is. Lead's boiling point, or let's say melting point, is 327.3 Celsius. So if lead changes from 300 degrees Celsius to 400 degrees Celsius, how much energy does it take? What you need to recognize is that lead melts at 327. So you would go from, what did I say, 300 to 400? You go from 300 to 327 as a solid, then you have the phase change, then you go from 327 up to 400 as a liquid. So the process we went over yesterday in class, that ending part, is really the only difficult math in Chapter 9. Okay? The other math part in Chapter 9 was converting temperatures. If you can't do that, please come see me at some point. I don't know, if you're free today or right after school at some point, but you should be able to convert temperatures easily. The math from Chapter 9, you can expect, for certainty, something with floating or sinking and buoyancy involved, some kind of a problem like that. I'm telling you now what the kind of problems you can expect are. You could expect something with Pascal's principle, like the hydraulic press, P1 equals P2, where F1 over A1 equals F2 over A2. And in that problem, you could expect to be asked to find like a mechanical advantage. So if you put in 50 newtons of force and lift something that's 300 newtons, that's a mechanical advantage of 6. 50 to 300 is a ratio of 6. You should definitely be able to use the continuity equation, which just says AV equals AV. If the cross-sectional area decreases or increases, what happens to the velocity of the fluid in a pipe? Or if it changes, what happens specifically, like a number. Or maybe that could be a multiple choice, but the idea for that is necessary. You should be able to calculate the pressure on an object at a certain depth in a fluid using P equals P0 plus rho GH. I'm trying to tell you the math problems because I'm not going to spend time going over all the math problems right now because it would take us 2-3 periods straight. So if you have trouble on Chapter 9 math problems and you were not here, I recommend A, watching that video and looking at the solution. If you were here, go to the actual textbook in Chapter 9. Take a look at some of the problems in there. If you want some example problems, feel free, I'm happy to email you a list of them. There is no problem set for this. So for those that usually use the problem set to help study, it might be useful to look at the textbook because that's really where the problems come from anyway. So look at some of the problems in Chapter 9. Maybe a problem that says like, I don't know, a weight of an object is this much. If its volume is this much, is it floating? Is it sinking? If the density of the fluid is this, you can determine those values. You can determine whether it sinks or floats based on the actual buoyant force. I'm trying to think of other stuff mathematically. That's it mathematically, but there's a decent amount for the fluid stuff. There's really only one thing for the heat transfer, and that's what we did at the end of class yesterday. Okay, the conversions from Fahrenheit to Celsius, that stuff, that it'll be included in math, but that'll be like a 2-pointer at most. There's not much to do with that. Maybe I'll have you convert, and then using that conversion, find out the Q value if a substance changes from X degree to another degree. I don't know, whatever it may be. Conceptually, we talked about things that you went over in your lab. That's a really good video to rewatch, the concepts there. So what happens to the pressure in an object as the depth changes, or as the density of the fluid changes, that was in your lab in the video you recorded. Or maybe what happens with the continuity equation, or Bernoulli's principle. Bernoulli's principle is what allows us to have planes, really. The concept of a pressure differential due to the velocity being different on the top and bottom of the wing. When that happens, you have a pressure differential which causes a lift force, which makes the plane take off. Trying to go through general concepts. The idea of apparent weight. What's apparent weight, really? Apparent weight is that...
It's the weight that you are versus the weight that you feel like you're in the fluid.
That's the buoyant force, the difference there. But the apparent weight is the weight you feel like you're in a fluid. So if I'm in a fluid, if I'm in a pool swimming, and I only feel like I weigh 100 pounds, and normally I weigh 160 pounds, well, the difference there is the buoyant force. So the buoyant force will be 60 pounds of force acting up. My apparent weight is 100. That's what I feel like I weigh. So if I know my weight is 160, and I know buoyancy is 60, I can determine the apparent weight by subtracting those two and getting 100 as an answer. Atmospheric pressure is the pressure weighing down on us from the atmosphere, hence atmospheric pressure. It's 101.3 kilopascals, or 1 times 10 to the 5th pascals. That quantity is summed with the gauge pressure to give you the overall pressure acting on an object. Okay, and that comes from this formula here. So this is the absolute pressure. This is atmospheric pressure. And this is your gauge pressure. The gauge pressure is the pressure exerted on a body due to the fluid above it, like the water or the liquid really. Atmospheric pressure is still a pressure due to a fluid, but it happens to be the atmosphere. And then absolute pressure just means the pressure felt with the sum of those two quantities. Absolute, overall, same thing. Okay, you could use either word interchangeably. Again, the hydraulic press is this, which really becomes this. And finally, the continuity equation is this. What does V stand for in this equation? Velocity. Velocity. Okay? You know this equation. I'll put it in the top right. It's on your formula sheet. But let's talk about it for a second. Rho stands for what again? Good. F stands for? What's subscript F?
Fluid.
Fluid. The density of the fluid times the volume of the fluid displaced. What is that, or what does that mean? Volume of the fluid displaced. Because people are still making mistakes with that. What does it mean, the volume of the fluid displaced?
Is it like if you had like a jar of water and you put like a golf ball in it, the volume of the amount of water that falls out after, if it was still at the top before?
Yeah. If you fill the cylinder with water to the top, or cylindrical object with water to the tippy top, drop an object in, whatever spills over will be the fluid displaced. So it's really how much of the object is underwater. If the object isn't fully underwater, say the object is only halfway underwater, the volume of the fluid displaced would be half of the volume of the object. Again, the volume of the object underwater is only like, say, 70%. Something like this. Let's say 70% of it is underwater. Okay, that's 70% of it is underwater. And you know that the volume of the object, say it's 10 cubic meters. That means that the volume of the fluid displaced is what? The whole object is 10 cubic meters as a volume. 70% of it is underwater. So what is it?
7.
So it's simply 7. It's not difficult math. If the volume of the object hypothetically were, say, 20 cubic meters, how much fluid would be displaced then?
13.
Double 7.
14.
14. Again, this is assuming in this case that 70% of the object is underwater. Remember, however much of the object is underwater is equal to the amount of fluid displaced. Okay? If the whole object were underwater, then the volume of the object is equal to the volume of the fluid displaced. When the entire object is underwater, so either it's at the bottom or it's suspended in limbo, VO is equal to VF. They're both the same value.
Why do you double them?
I just did 70% of 20, which is 14. He gave me 7 for 10 as an answer, so when I double this, if you double that, you get the same answer. So 70% of 20 is 14. Okay, but that was just mental math I was trying to go through there. Let's see. I'm trying to think of what else. What is the difference between a liquid and a gas? A liquid and a gas, because they're both fluids. What's the one difference? A gas does not have a definite volume or shape, really, right? Okay, liquid doesn't have a definite shape, but liquids have a definite volume. And liquids take on the shape of their container. Okay, that was the stuff we talked about in the beginning of 9.1, the very.
The gas is
A gas will if the container can hold it. Keep that in mind. Like, if I have water in a cup and I start to boil it, the gas will just float off. the shape of the container is kind of like the room, really. But if there was a balloon above it, it would fill up that balloon. Yeah, but it would need to be like an inverted shape, whereas a liquid would be a shape that is open with the top open, because gravity pulls the liquid down. Let's see. You should know all of these three things that we talked about in office hours yesterday. But if you have three scenarios, I'll do them real quick. An object on the top, an object in the middle, an object at the bottom. At the top, it means that the density of the object is clearly less than the fluid for it to float. If it's in the middle, the densities are the same. If it's at the bottom, the density of the object is greater than the fluid. Okay, those three things should be apparent automatically. Automatically. Okay, if you had like 7 oils in a container and you saw different layers, they separate based on density. The highest oil has the lowest density. The lowest oil in the container has the highest density. You should also know that at this point, the buoyant force equals gravity. Same thing here. But when it's sunken, the buoyant force is less than gravity. Okay, the first two are the same, really. Okay, the buoyant force and gravity are equal to each other in both of those scenarios. Now, if it requires a force to hold this object where it is, see where this object is right now? If it requires me pushing down to hold it there, it means that the buoyant force is less than gravity still. I'm sorry, greater than gravity still. Okay, and when I let go, though, what will happen? It'll pop up to the surface, and it'll land at the top, and you'll have this case now. Okay, again, this is if the buoyant force, for some reason, say the buoyant force exceeded gravity. Let's say this is our free body diagram, hypothetically. It would require me pushing down on the object, or you have to like tether this to the bottom of the floor. We did an example of this in class where a chain linked this. There was a chain from here to here. Okay, there was a chain linking it to the bottom floor, which meant there was tension, Ft, in the chain. So in this case, if buoyancy was say 100 newtons pushing it up, with gravity only pulled down with 50 newtons, then the chain would need to pull down with another 50 newtons to counteract buoyancy. If that chain was cut, and buoyancy was 50 or 100, and gravity was 50, there'd be a net force of 50 upward. Okay, net force of 50 upward. And theoretically, if you knew the mass of the object, again, let's see buoyancy is 100, and let's say the weight of it is 50, hypothetically. If this were the case, and the tension would clearly be 50 now, right? This is one of those cases where it's a different case than these three, and you cut the tension out suddenly, you cut the cable, it means that the overall net force would be 50 newtons upward. So you could say F equals ma if you wanted to. You could say 50 equals, and say you knew the mass. Say the mass is 10 kilograms. You could figure out the acceleration of the object shooting up out of the water. Okay? You've seen this before. Take a beach balloon, right? Beach ball. Beach ball. Hold it under the water and let go. It shoots out of the water, right? That's what you're seeing here. If this was the net force pushing up, and this was the mass of the beach ball, which would be much less than this, you can determine the acceleration. Let's see. Yes. Right now?
Yeah.
Okay.
You could have just said you have to go. I didn't catch my
There are two types. Be safe. There are two types of flows. There are two types of flows with fluids we talked about. What are they called? What are the two types of flows that a fluid can have? One is very predictable. One is very unpredictable. Remember the fluid flow over like a surface? It can be very smooth and predictable versus you can have these little eddy currents behind it. Like the ripples? Yeah, but what's the two types of flow? What are they called? Really? What makes a plane shake? We talked about this. What is it? Yeah, so one flow is called turbulent flow and the other was called?
Deviation.
You guys need to study. Just because there's no problems, that doesn't mean you shouldn't have studied last night.
Well, that's not like a...
Problems that always helps you 2 nights ahead, right? That's why I give them to you. What's the other type of flow? Look in your notes, come on. So it's an L.
No. Leak.
What is it? Julia gets? I said, look in your notes. That's what I said. She just don't listen. What is it? Laminar. Laminar flow. Laminar flow simply means flow that is predictable, that is non-turbulent, that does not exceed a certain Reynolds number.
Oh, Reynolds.
Remember I talked about the Reynolds number. If the value of the flow's Reynolds number is lower than a given value, it is laminar flow. If the Reynolds number is calculated to be greater than some threshold, it is called turbulent flow.
Turbulent flow is equal to that.
Stop giggling back there. All right. Let's say hypothetically, I told you the following. You walk into a room, okay? I'm not telling you what the temperature in the room is. You walk into a room, and right away, heat travels from your body to the room. What can you conclude?
It's a really cold room.
The room has to be colder than their body. Really cold is a vague term, right? So you can make a conclusion that the room is clearly colder than your body. Whichever way heat flows is always from hot to cold. And hot and cold are, again, relative terms. Something is hot to a human, it may not be hot to a machine. Something that is difficult to touch for, I don't know, an alien race might not be for us based on our body temperatures.
Does that mean that cold flows from hot?
No, cold never flows, guys. Again, cold can never flow. Only heat flows. So whatever happens, if there are two things at a different temperature, the energy change will be from the hot object to the cold one always. So again, that's like when you touch this ledge here. What's happening? It feels cold to me.
Transferring
From where to where?
heat.
The hand to the thing. Which is why the thing, the ledge here, will be warmer if I touch it a second after. I'll feel the warmth that was left behind. What objects or what materials are good conductors of thermal energy? Good conductors of thermal energy. Examples are metals. What are good insulators? Gases. That's why we have double pane windows, like I alluded to. There's a gas trapped in there that acts as an insulating barrier. Glass can easily transmit heat through, whereas gas, not glass, but gas prevents heat transfer. What are the three types of heat transfer? What are the three types of heat transfer? Radiation is one. That's when EM waves travel from one body to another. There's no transfer of matter here. It's EM waves. The object radiates energy in the form of EM waves, which lowers its internal energy. If we didn't radiate energy and our heart kept pumping the way it was, our body would overheat. That's why you radiate heat. That's why you're giving off heat. It's an exothermic process that your body is always undergoing. Obviously, until you're cold and you have to get in the room to warm up, then you become an endothermic body. Until you warm up enough and your body starts to radiate heat again. Even while you're absorbing heat, though, you are still radiating some. What else? That's radiation. What are the other two modes? Give me one of them. 3 modes of heat transfer, very important. Conduction. Conduction occurs within a single material or within a single material. Like I touched that with this desk, it starts to warm up the desk via conduction. Okay, the desk starts to heat up, it heats up the rest of the desk. So it happens within one material or between two materials that are, what is it? In contact or touching, good. Conduction involves contact. Conduction involves contact. How about convection? And by the way, conduction, we talked about something called the K value, which is the conductive coefficient. Higher K values for materials means they conduct heat more easily. What about convection? Convection. There is some conduction involved in convection, actually, but we didn't really go into that.
Wait, higher K values conduct what? Can you say?
More heat. Now,
It's the movement of molecules in the fluid so that result in heat transfer.
yeah, it's the fluid flow that results in heat transfer. Okay? So whether a fan is blowing over a surface or a fan is blowing over a heat sink in a computer, or you have liquid nitrogen running over some sort of a server to cool it off. Or you look at like Mr. Freeze from Batman, where he's got like fluid flowing all around and he's like frozen. That's really what convection is. Okay, evaporation is a form of convection. And you learn like 8th grade science, you see like the flow of evaporation. You see that like cyclical flow. That's the same way convection occurs. Okay, hot fluid rises to the top. The cold replaces it at the bottom, and it continues this flow. Take a look. Air conditioners, where are they in the windows? What do you notice? Why? What will happen if the cold air comes in? It'll sink down, which will cause a flow. It makes sense for air conditioners to be higher and heaters to be lower. It's not like coincidental. The hot air coming out of the radiator rises to the top, which creates convective flow in the room, which tries to come to a better temperature over time. Okay, that's the reasoning for that. It's convection for you. What is thermal equilibrium? What is thermal equilibrium? Summer.
Like if you put your hand on the cold thing, and once your hand transfers enough heat onto that thing, they become the same.
Yes, they become the same temperature. Okay? Two bodies in contact that eventually become the same temperature, that were initially not the same temperature. That's where thermal equilibrium occurs. Yes, John?
Wouldn't your part of your body not work for that though, because it's always emitting heat?
Now, what would happen was the temperature of the ledge would rise up enough to match your hand.
But your hand wouldn't go down.
Your hand would go down, yeah, absolutely, but not significantly. Try it. I mean, when I touch my hand now, it's cold. My hand feels cold. So the surface of my skin can go down. It's not going to affect it. When you measure your body's temperature, you're measuring, remember we talked like under your tongue when you use a thermometer? You would never measure your skin. Your skin is not 98.6 degrees. That's a common misconception. Your skin is not 98.6 degrees. It's much less than that. Because it's constantly there's convection around you right now. There's fluid flow around you at a cooler temperature. So it's never at that temperature. So when you touch it, it will cool it off until it gets cold enough that these are in equilibrium. And then when I remove it now, I'll feel it's cold, but eventually it'll warm back up, and this will cool back off.
So if we were in like a sealed box and the temperature was 98.6 degrees, and there was no humidity, would we be
Our skin would start to actually heat up, because our body internally is 98.6. Your skin is not.
What is our skin temperature?
I don't know.
Which is very...
We could try it. I mean, the thermometer's in the chem room. Somebody want to run into the chem room and grab a thermometer real quick? You could just put it on your skin and try it for like 10 minutes and see. I don't know. I'm not sure what it would be. I don't know. If Mr. J's next door, you want to ask him where they are, but if you know where they are in the chem room from last year, just grab a thermometer, come back in.
That's crazy.
I'm not sure. It's actually a good question. But I can tell you guys that your body is constantly radiating energy. Your internal core temperature is higher than your actual body temperature. Okay? All right. We talked about in class, and I had you guys, some of you do the demo where you added salt to water. What did it do to the water when you added salt to it?
But it made the water a lot denser.
Good. It fogged it up, but it made it more dense. That's the key. And that's why the egg rose up to the top. So when you add a solute, listen, when you add a solute to a solvent, what happens is you're increasing the density. You add sugar to water, you're also increasing its density. Because now you have a solid that's mixed in with it. It's probably in the, is that in there? Alright, maybe I'll try and check it out and sit later. So when you add a solid substance to a fluid like a liquid and it mixes in a homogeneous mixture, not heterogeneous, a homogeneous mixture, you get an increase in density. Okay, that increases the density of the actual fluid.
Wait, is homogeneous on the test? What is that?
No, it just means, I'm just giving the example, like when you mix salt water and it all absorbs into it.
Alright.
We talked about pressure and force and how they're related. So for example, why does it hurt when I prick myself with a pin very lightly versus taking this pen? And I take the pen, apply the same amount of force. Look, it's not hurting at all. If I took a pin and did that, what would happen? Yeah, it hurt a lot. What's happening? Can't. What is it? Yeah, the area of contact. Very good. So what's happening when I use a pin? It's much less area. If there's much less area and I apply the same force, a lot more pressure. How can I show it? P equals F over A. If you reduce the area, right, the area is in the denominator. Reduce it. What has to happen to the pressure then? Has to go up. They are what related?
Inversely.
Inversely. Assuming the force is held constant, if you decrease the area of contact, you're increasing pressure. I did the example where I stood on 2 feet, and then I said, if I stand on 1 foot, now it's double pressure on my foot. Same force, my body weight is the same. Okay, but I'm doing double the pressure now over here. All right. How does a thermometer work? How does a thermometer work? Whether it's a choice or short answer, you should be able to have an idea. Nobody knows how a thermometer works. What? We went over this in classes.
Due to heat, the bulb is going to expand and just
Why does it stop at a certain point? You're right so far. Very good. So when you induce or increase the heat or the temperature of the fluid that's in the bottom of the thermometer in the bowl of the thermometer, thermal expansion tells us when you increase temperature, volume increases. So the fluid rises up the container until it reaches thermal equilibrium, and it stops. Okay, when it reaches thermal equilibrium, the fluid in a thermometer stops rising toward the top. All right, let's quickly do a math example from yesterday to make sure that we're certain about this for the heat, or what's the word? For latent heat of fusion and vaporization. So let's say, I'm going to tell you these values real quick. Let's say we know we're looking at aluminum. Aluminum's melting point is 660 Celsius. Its boiling point is 2467 Celsius. This is aluminum. If we have aluminum and its temperature is changing from 220 Celsius up to 700 Celsius, tell me physically what's happening. Step 1. What happens first? Dirks. The temperature goes first from 220 to 660, and while that's happening, it remains a solid, right? What happens at 660, Dirks? It undergoes a phase change. It doesn't change temperature. It undergoes a phase change at 660. Then, once it's all now no longer solid, it's all liquid, it goes from 660 to 700. So in this case, there's Q1, Q2, and Q3. If it went from 220 up to 2700 instead of 700.
4 Qs.
5 Qs. Careful, 5. It's a solid from 220 to 660.
Yeah.
Then it undergoes a phase change to a liquid. It's a liquid from 660 up to 2467. Then it undergoes a phase change from a liquid to a gas. Then it's a gas from 2467 up to 2700.
How do you know when phase changes happen?
The boiling point and the freezing point of these materials is given in the table.
Oh, okay.
I told you before I started this problem
Yeah,
that this is called the freezing or melting point.
Okay.
This is called the boiling or condensing point. Okay? It's in your table. Look at your notes. I guarantee you that you need to practice this. It will be on your test. It will help you practice. If you don't, it's going to take you a lot longer. You're not going to finish your test. This is a longer test. It's an 8-day enrollment paper. But it's definitely a longer test than the past ones. I'm telling you now, to give you a heads up. You need to be familiar with these tables. If you spend 10 minutes on this problem, you're not going to finish the test. This, honestly, the math minus problem, 3 minutes at most. That's all this problem should take you. You really should. It's MC delta T, ML. MC delta T, ML. MC delta T. Add all 5 Q's together, you get your answer. Email me if you want any sample questions. I'll email you some problems. That's fine.